So today we want to begin our discussion of nuclear reactions. Whenever you have high energy particles or waves that are emitted from an unstable nucleus, we call that process radioactivity. Now, when those particles are emitted and that changes that nucleus of the atom, the process is known as radioactive decay or transmutation. And you end up with a formation of different or of atoms with different identities. Now, if you emit waves of energy, it doesn't change the identity of the atom, but it does lower the overall energy of that atom. Now, radioactive isotopes, or what are sometimes called radioisotopes, are elements that emit radiation. So the symbol for a particular isotope, remember we've covered this before, but I want to review it. You can write it as this symbol right here, where X is the element symbol, A is the mass number, and remember the mass number is the protons plus neutrons. So that means that A, this number on top, is always the biggest number. So keep that in mind. The atomic number is going to be on the bottom for that particular element. So let's say that we want to know what the symbol for an isotope of cobalt would be if it had 33 neutrons. Well, first of all, the symbol for the element cobalt is CO. Now, the fact that it has 33 neutrons, notice nowhere on here does it ever specifically give you a place to put the number of neutrons. So the number 33 is not going to show up. However, the atomic number of cobalt will, and if you look at the periodic table, you'll see that the atomic number of cobalt is 27, the number of protons. Now, once we know that, remember, just simply adding up the protons plus the neutrons, so that 33 plus the 27, it's going to give us a mass number of 60. So we can write cobalt with 60 over 27 for the symbol. You will sometimes see just 60 on top for cobalt because all cobalt atoms obviously have 27 protons. The name will also be written with just the mass number. So you'll see cobalt with a dash and then 60 out after it. So keep that in mind, that those, just like I said, a reminder from Chem 1 about what those symbols are supposed to look like. Now, in Chem 1, we talked about three major types of emission. So the first three are going to be reviewed: alpha, beta, and gamma emission. But I want to go over them anyway because it's been a while. Alpha, which has that written symbol, looks more like a fish, but that alpha symbol stands for a positively charged helium nucleus. It is positively charged. It's simply a helium nucleus with both of the electrons missing. Now, this is kind of like the 18-wheeler of the periodic, or of the radioactive particles. It's really big, and therefore it's got a low penetrating ability. It doesn't penetrate very far. Now, if you ingest it, then it's a definite problem. But even skin will block alpha radiation. Since it's so big, very large elements, that's going to be their decay method of choice. Elements above bismuth are all unstable, and they tend to undergo alpha decay whenever they do decay. Now, notice what happens in a nuclear reaction. Remember, if we treat that arrow as an equal sign, then the particles that add up on top must equal on both sides. So on top here, we've got 247 and 4. That's going to give us 251 on top, which must match the 251 on the top on the other side, which it does. On bottom, we've got 96 and 2, so we've got 98 on bottom, which does indeed match the 98 on the other side. So those must match up. And in a little bit, we'll do some examples of ones where we have particles missing, and we have to determine what that other missing particle is, and that's how we're going to do it. Beta radiation, or beta emission. We have the symbol beta. It's an electron. It's negatively charged. That 0 over -1, the 0 on top stands for the fact that it doesn't have any protons or neutrons in it. Now, the -1 on bottom, obviously it doesn't have a -1 proton, but it just is an indication of the charge. It just kind of helps us keep track, like a bookkeeping method, of what's happening to the particles. Now, if you have too many neutrons for stability in our nucleus, because keep in mind the nucleus is made up of positive protons and neutrons, and those positive protons don't want to be next to each other. Electromagnetic force of attraction says repel, but they're being held together by the strong force. And if we get too many neutrons in there, it can break that down and cause um, instability. So if that happens, if we've got a high neutron to proton ratio, too many neutrons, it tends to undergo beta decay because look what happens. And keep in mind that if you say decay, emission, if it gives off, um, all of those are an indication that the particle in question is on the right-hand side. So we've emitted a beta particle, and in doing so, look what happened to the nucleus of our atom. We ended up with an extra proton. And simplistically, I know lots of people that don't like it described it like this, but if you think of a neutron kind of as being a proton and an electron melded together, then it makes sense that if you got rid of the electron portion, you'd leave the proton behind. It works well because you change a neutron, you're losing a neutron and gaining a proton in the process when you give off that electron. The third one, gamma radiation, and it looks like this when it's handwritten. It's chargeless. It's a wave of radiation. It's neutral in charge. Very high penetrating ability because it's not a particle. It's a wave. This does not change the identity of the atom, but it does lower the energy whenever that radiation is given off. So those are the three we covered last year. Now for the new ones that we're going to look at and include this year, we have the positron. Positron is a positive electron. I know that sounds weird. It's the antimatter form of the electron. It has moderate penetrating ability. Generally, you're going to see it written as 0 over positive 1 e, but you could also see it as 0 over positive 1 beta. I tend to use the 0 over positive 1 e whenever I write them in equations. Now, if you have too few neutrons for stability, and that's an issue as well, in other words, a low neutron to proton ratio, then we tend to undergo positron emission because look what happens. If you get rid of a positron, we lower, and by the way, this is wrong. This should have a 40 on top instead of 14. So let's change that real quick. But if you give off a positron, you actually end up with one less proton and an extra neutron in the mix. So you've increased that neutron-proton ratio if it's too low. So that works well for positron emission. Remember, emission means the particle's on the right-hand side. Now, having a situation where you've got a low neutron-proton ratio can also be resolved by something called K capture. Now, capture, absorption, those terms indicate that the particle in question is on the left-hand side because it's being captured or absorbed. So notice that the beta particle, in this case, not the positron, the beta particle is being captured, and by being captured, notice what happens. We lower the number of protons again and increase the number of neutrons by 1. So again, it helps resolve that low neutron-proton ratio. The next particle is the proton. The proton, I will generally write it as 1 over 1h, but you'll see it as 1 over 1p very often. A proton, remember, if you think about a hydrogen atom, the normal hydrogen, all it has in the nucleus is a proton. And roaming around out here is an electron. And if you get rid of that electron, all you've got is a proton. So we think of a positive hydrogen ion as being a proton. They're used interchangeably. So in this bottom one, we notice another example. We've got two carbon 12s colliding here on the left-hand side. And when they do, they form a sodium 23 nucleus and give off a proton in the process. So this would be proton emission or proton decay, if you will. And finally, the neutron. Notice the symbol for a neutron is 1 over 0. There are no protons in it, but it has one neutron. It's a neutron. So we have a 1 over 0 n for the symbol. And an example of this would be the case here where we collide or we shoot some deuterium, some hydrogen 2 um, particles at some molybdenum 96. And when we do, we end up with technetium 97, and it gives off a neutron or emits a neutron in the process. So those are the 6 different examples of particles I expect you to know. There are lots of others, but those are the ones that I expect you to know, and it's the ones that you'll encounter at the AP level. So if we're going to complete something like this, look at what happens here. We've got platinum 190, and it's undergoing alpha decay. If you notice, it's got that alpha particle being given off on the outside. It's emitting an alpha particle. And if we add up to get 190 on the right-hand side, we've got 190 on the left. Looks like we need 186 on top here. And since there's 78 on the left-hand side, and we've already got 2 accounted for from helium, looks like we're going to need 76 for our atomic number on the bottom. Now we simply look up on the periodic chart, and we see that number 76 is osmium. So this is osmium 186 is the daughter nuclide that we form during this process. Same thing on the next one. Remember to treat that arrow, both cases, like an equal sign. So we need 161 on top, and since this is already a 0, we're going to leave the 161 on top. Be careful. This one messes people up all the time. They're continually putting 64 on the bottom in a situation like this. But you're subtracting 1 here, so make sure that this bottom number ends up being a 66. So 66 minus 1 gives you the 65 on the other side. Now, number 66 is, if you look it up on the periodic table, is dysprosium. So dysprosium 161 is the product of this reaction. So one of the things that you'll be doing on your worksheet is going through and doing several equations like this and finding out either what particles emitted or what daughter nuclide is formed. Now, when we look at stability of a nucleus, we have something called the band of stability. Now, this line going through here is just a line that indicates that the number of neutrons and the number of protons are equal. Notice at the very beginning, when we have our really small elements, that having a relatively equal number of protons and neutrons is desirable. That's where our stable nuclei are located. But notice what happens as you get further and further along as far as size is concerned. The bigger and bigger you get, the further and further above that line you get in order to increase stability of those bigger elements. You need more neutrons present in those bigger elements to make the nuclei stable. So you can see that this whole range right here, this black range here, this is our band of stability that gets, again, further and further away from equal numbers of protons and neutrons as you get bigger and bigger atoms. So this is just a table of the abundance of natural occurring isotopes, and you'll notice that the most stable situation is when you have an even number of protons and neutrons. There are 157 stable isotopes that have that configuration. What's so odd to me, is that if you have both an odd number of protons and an odd number of neutrons, look at the number of stable isotopes. There are only 4. Somebody else besides me may know the answer to that. I don't, but I just think that is so incredibly fascinating that just because there's an odd number of protons and neutrons, we have such a low stability of isotopes that have that configuration. So it's pretty interesting. Now, some things to remember. All elements beyond bismuth are unstable. They're radioactive. There's no such thing as a stable nuclide of an element bigger than bismuth. Generally, as we mentioned before, they undergo alpha decay because that's got the biggest bang for its buck. It's going to be able to change its identity very rapidly by giving off alpha particles because it's giving off 2 protons and 2 neutrons all at once. If we have smaller elements that have too many neutrons, and I call that bunches of neutrons. This is my little mnemonic device to remember. Bunches of neutrons then too many neutrons means I'm going to go through beta decay. Bunches of neutrons, beta decay. AP expects us to look at some of these isotopes and be able to tell what kind or predict what kind of decay process they're going to go through. Smaller elements, they have too few neutrons, and I call these puny neutrons. Puny neutrons is going to give me positron emission. And if you'll remember back when we were talking about earlier, we get an equivalent result from positron emission as we do from K capture. And if they ask us about this one, just pick one. It doesn't really matter. Either positron emission or K capture will work to help fix a situation where we don't have enough neutrons. Now, how do we know if we have too many neutrons, too few neutrons, etc.? Well, the first thing that I always do is to look at the mass number. And if you look at this first one, cobalt 60, and you look at the average atomic mass, which is 58.9. So we've got an average atomic mass for cobalt 60 of 58.9. Let's just call it 59. Cobalt is stable. Okay? That's the weighted average. Remember the atomic mass, the weighted average of the masses of those nuclides, of all the isotopes of cobalt. So 59 is considered stable, or it's where the average is. But this has cobalt 60. So it can't have more protons. It's got 27, no matter what mass number it's got, it's going to have 27 protons. So if we look at this situation, it looks like cobalt 60 has too many neutrons. It's too big. We can't do anything about the protons because cobalt is cobalt, but it has too many neutrons. So what do we do when we have too many neutrons? Remember, that's bunches of neutrons, which is beta decay. So that's what you want to show for this is beta decay. So we start out with our cobalt 60. Remember, if it's decay or emission, we're going to put the particle on the right-hand side. So beta decay means our beta particle, which is 0 over negative 1e, is going to go on the right-hand side. Remember, cobalt has an atomic mass of 27, so that means we need a 28 here, and the 60 will stay the same on top, and this is nickel. So by beta decay, we would gain another proton, lose a neutron, and we would help that too many neutron situation. So this is beta decay. The next one, nitrogen 13. It's a smaller element, meaning it's less than bismuth. So we need to look at what normal average nitrogen is. And if you look up nitrogen on the periodic table, normal is about 14.01, so call it 14 nitrogen. But notice nitrogen 13, our target nuclide, is too small. Now, they both have 7 protons. We can't do anything about the protons. So evidently, nitrogen 13 has too few neutrons. It's too small. So if it's got too few neutrons, then I call that puny neutrons. So remember, if you have puny neutrons, you can either do positron emission or K capture. And I'm going to show both. Positron emission or K capture. So positron emission, I'm going to give off that positron on the right-hand side. I'm going to start with my nitrogen 13. I'm going to give off a 0 plus 1 electron on the right-hand side. And in order for that to equal out, I'm going to need the 13 on top and a 6 on the bottom So we're going to end up with a daughter nuclide of carbon-13. If we do K-capture, K-capture, remember, is taking a beta particle and adding it on the left. Capture means that the particle goes on the left. K-capture is capturing an electron. They used to call the K shell used to be that first energy level of electrons, and K capture was talking about grabbing an electron from that first energy level. But when we react this, we end up, notice, with the same daughter nuclide. So whether we choose positron emission or whether we choose K capture, we end up with the same daughter nuclide. Finally, the last one, americium-243. It's bigger than bismuth. It's going to tend to undergo alpha decay because it's so big. So alpha decay means the alpha particle is going to be on the right-hand side. So I'm going to put that 4/2 He on the right-hand side. We're starting with americium-243. Americium has an atomic number of 95, so that's going to go on bottom. And it looks like we're going to need to have a 93 over here for our bottom number to go with the 2 from the alpha particle, and on top a 239. So we can add up 239 plus 4 on the right is going to give us our 243 on the left. Number 93 is neptunium. So our daughter nuclide is going to be neptunium in this process. And again, this was alpha decay or alpha emission, either one.